So you are University of Wisconsin, or
Yeah.
Wisconsin Medicine, or
Yes.
Wisconsin?
Yeah,
Should I say
both? You can say whichever one you prefer. Wisconsin Madison, if you want. Since most people don't know where Wisconsin is.
Okay, I think we should start. Yeah, sure. Okay. Sorry about that. Today we start with Andrei Caldararu, whom I know for at least 18 years. So he was a mathematician, and now you have him at string theory, as you see. So he's from University of Wisconsin, and he will tell us about categorical enumerative invariants.
Thank you very much. Thank you to the organizers. This is my second time speaking at the strings conference. I am pretty well convinced that the previous time it was in the last century. It was a University of Pennsylvania. I was actually curious, but I could not figure out when it was. Anyway, so I'm going to talk about some joint work with my former student, Junut Tu. He and I are the main collaborators on this project, and various kind of offshoots of the project are with Kevin Costello and with C. Lee, and several of my students, current students, are working on problems about this. So it's a large project that has lots of stuff for everybody in it if people are interested. All right, so I want to begin with some history by way of motivation of the problem. So in the 1990s, in the early 1990s, people discovered applications of mirror symmetry to mathematics, and mathematicians suddenly got excited about this. The paper that started it all for mathematicians, at least, was this 92 paper by Candelas, De La Osa, Green, and Parks, where they managed to compute this sequence of numbers that was tantalizing for mathematicians, because we were only able to, I'm speaking we in the name of mathematicians, we were only able to compute with great difficulty, I think, the first three, and we made a mistake when computing the fourth one. And so the fact that these people predicted correctly this sequence of numbers, and in fact could compute all of them very quickly, was amazing to mathematicians and started it all for us. These are the Gromov-Witten invariants of genus 0 of various degrees of a quintic Calabi-Yau threefold. And the way Candelas, De La Osa, Green, and Parks computed these was done by not computing the numbers themselves, but by calculating a solution of the Picard-Fuchs equation. The Picard-Fuchs equation was very well known for mathematicians, but it was a Picard-Fuchs equation for a different Calabi-Yau manifold, for a family of Calabi-Yau manifolds, which are now called the mirror quintics X check, and I've put a psi there to signify that it depends on a parameter. So while the original Calabi-Yau threefold, you can take any quintic you want, you'll always get the same numbers. The quintics, the mirror quintics, you need to keep track of the parameter, and you need to know the whole family in order to calculate those invariants. All right. Then 1994, amazingly soon after the original paper, Kontsevich got his Fields Medal and stated this amazing conjecture called, which we now call homological mirror symmetry, which said that the relationship between the space X that we started with, the quintic, and the mirror X check, is that there should be a way to match the parameter psi to another parameter rho. The mirror map is actually complicated. This psi corresponds to rho, but I didn't give it any name here. In such a way that when you compute the derived category of coherent sheaves on this specific Calabi-Yau X check with coordinate at the particular value of the coordinate psi, you should get something called the Fukaya category of the original space X evaluated at rho. So the Fukaya category, you might remember, depends on some kind of it's a category over the Novikov ring. We think of this rho roughly as parameterizing the volume of the symplectic form. I'm not going to dwell too much on this, but intuitively, the Fukaya category should also depend on a parameter, and you should match this parameter to the psi parameter. Somehow the psi is the complex structure parameter, rho is the symplectic side, the Kähler modulus. All right. What was implied in Kontsevich's conjecture? If you see this conjecture at first, you might ask yourself, well, this has absolutely nothing to do with those numbers that we saw before. Previously, we calculated some numbers. Now we've said there are some categories that are equivalent. How are those two statements related? Still, Kontsevich implied in his talk that homological mirror symmetry should somehow essentially tautologically imply enumerative mirror symmetry. So the equality of some numbers calculated in two different ways. On one side, Gromov-Witten invariants, on the other side, expanding some solution of Picard-Fuchs. So it's amazing that it's now almost 30 years since then, and we still don't have a full proof of this thing. But what I'm going to talk about today is towards understanding this conjecture. So what was the intuitive idea? Why Kontsevich predicted this? The idea is that maybe I'm going to state this intuitive idea in a way that we now know is not exactly correct, but I will just state the simplest form of it. Somehow, let's assume for a second in our mind that for every Calabi-Yau category over the complex numbers, not over the Novikov ring. So just like the derived category of a quintic threefold, let's say of a specific quintic threefold or of any other Calabi-Yau threefold, let's say you could associate a number somehow, which I'm calling F0 of C. And maybe in principle, there should be such a number for higher genus as well. That's why I call it F0. You could take this invariant and compute it for various derived categories. What you should get then is a function which depends on psi, on which Calabi-Yau you took. So you should end up with a function defined on the moduli space of Calabi-Yau threefolds. This should be what Candelas, De La Osa, Green, and Parks found as a solution of Picard-Fuchs. It should be something describing the variation of Hodge structures on this family X check. On the other hand, it should be somehow tautologically the case that if you calculate this for the other category, Fukaya of X rho, for this particular value of rho, you should get, as you calculate it for various values of rho, you should get a function that depends on rho, which should be the generating power series of Gromov-Witten genus 0 invariants. This was the intuitive idea behind Kontsevich's implied conjecture. And where does this connect with homological mirror symmetry? Of course, the fact that we said that the derived category of X psi check is the Fukaya category of X rho, and this invariant F0 is an invariant. It depends only on the category that you inputted. The two functions will end up being the same under the mirror map psi matching with rho. This is how homological mirror symmetry would imply enumerative mirror symmetry. you end up with those two functions. They're the same. On one side, you can compute it by solving the Picard-Fuchs equation. On the other side, you expand it with respect to some coordinate, and you end up with Gromov-Witten invariants. Now, this approach, as I've described here, has many different issues. The first one being, it's not clear at all how to define this function, FG of C, which only takes into account a category C. An important question would be, if you did this, can you feed into this process some other categories, like the categories of matrix factorizations? What kind of answers would you get? We know that for F0, for the derived category, you should get the variation of Hodge structures. F0 of a Fukaya category, you should get the power series of Gromov-Witten invariants. What would you get for matrix factorization categories? Another question. On the B model side, we have no idea, at least we as mathematicians, we have no idea what should be the corresponding invariants we should get that should be analogs of higher genus Gromov-Witten invariants. So on the A model side, we have Gromov-Witten theory, which the definition is uniform in all genera. You take genus 0, 1, 2, 3, you define invariants. On the B model side, in genus 0, we have variation of Hodge structures, but for higher genus, we have nothing analogous that would recover the higher genus Gromov-Witten invariants. Another issue, in Gromov-Witten theory, if you're not on a Calabi-Yau threefold, and you still want to compute something, you want to compute some more complicated partition function, which involves insertions. And the things that you insert are either cohomology classes from your target manifold or psi classes from the moduli spaces. These tau I1 up to tau IN correspond to insertions of psi classes. These are called gravitational descendants, and these make perfect sense in Gromov-Witten theory. The question is there some analog when we deal with a category? The final point, which is maybe the most delicate one, and this is the one I'm going to try to hammer on the most today. When you discuss mirror symmetry, it was realized very early on that a space does not have a unique mirror. When you talk about mirrors, you talk about mirrors near a large complex structure limit point. So what you have on the Fukaya side is kind of naturally associated with the degeneration of the Fukaya category. When you look at the complex structure, you need to see a similar degeneration, and that corresponds to choosing a large complex structure limit point. But in the way I've described the story here, this large complex structure limit point does not enter anywhere. So the question is there some place where this thing needs to enter in the categorical theory? All right. So actually, I'll try to give some quick answers. So let me just give you a preview of what's going on here. This FG of C was defined, and I will say a few words about this, but the definition is very complicated. This is essentially the main result that we have, that you can define such a categorical definition of some invariants, and in fact, including insertions. So points 1 and 4 here are, the answer is yes. And I'm going to tell you very little today about how you do it, but you can read the papers. That's maybe not a good thing to say. For categories of matrix factorizations, you get what we would call B model FJRW invariants. You can put in also wrapped Fukaya categories and get A model FJRW invariants, so classical FJRW invariants. The answer to the question 3 is what is the analog of a variation of Hodge structures for genus greater than or equal to 1? The answer is these invariants that we define. So somehow what you should think of as that this thing, this categorical enumerative invariants that we define, if you apply this to a family of derived categories, that you should think of the answer in higher genus as a generalization of a variation of Hodge structure. And finally, the last point is one that I will belabor more, so I will discuss a lot more about this. All right, let's go back to the history and move to the early 2000s. And the first result that was important was a classification of two-dimensional extended topological field theories by Kontsevich, Soibelman, and Costello. And they said that if you want to classify two-dimensional extended topological field theories, you need to, to give one of those, it's equivalent to giving something called a smooth cyclic A-infinity algebra. I will say a bit more about what an A-infinity algebra is on the next slide, but I want to say that this statement is a complete analog of what people are familiar with, that if you want to classify topological two-dimensional field theories, so purely topological, you only care about that, you put no conformal structure whatsoever on the surfaces, you only have topological surfaces with boundary. In order to classify these, you need to classify Frobenius algebras. So a smooth cyclic A-infinity algebra is word for word the same thing as a Frobenius algebra, just extended homotopically. So in some sense, you take the second statement here, you just put homotopy everywhere, and it becomes the first statement. Now let me maybe try to say a word or two about what is a two-dimensional extended topological field theory. So in classical field theory, you have objects, you're looking at functors from a category of Bordisms, and in this category of Bordisms, the morphisms are circles. I'm talking about purely topological field theory. Morphisms are circles, and the objects are circles, and the morphisms are surfaces with boundaries, topological surfaces with boundary. In an extended TFT, you need to change this a little bit, namely, the circles end up being framed. So you need to put a framing on the circles. That essentially just means that on each boundary circle of a surface, you're going to have a marking, a marked point. And the other thing that you're going to do is, when you're talking about extended, is what it means is you're going to allow conformal structures on the surfaces that bound circles. However, you're not going to care about the specific realization of this conformal structure as such, but you're going to study the topology of the moduli space of conformal structures. So what that means, let me maybe try to write this down somewhere here, if there's some chalk. Oh, okay. So what a 2D extended TFT gives you it gives you maps, evaluation maps, Z, from chains on MGKL framed. So let me maybe write it like this first and then. So it gives you a DG vector space L, so vector space, graded vector space with a differential, and maps like this from the moduli space of framed Riemann surfaces of genus G with K points marked as inputs and L points marked as outputs. And you think about this as taking elements of this DG vector space and inputting it on the input points and reading off outputs at the output points. And it is the presence of this chains here that makes it a topological field theory as opposed to a purely conformal field theory. So you don't take into account the moduli space of conformal structures, which is this guy, but only the topology here. So this chains means singular chains. All right. So the theorem of Kontsevich and Soibelman and Costello says that if you want to give me one of those topological field theories, all you have to do is you have to give me a smooth cyclic infinity algebra, which is some kind of combinatorial data that can be described in very concrete terms. All right. Notice one thing here that's very important is that over here, there's no bar. So what you should think of as somehow this theory allows you to integrate over chains in the moduli space, but tells you nothing about how to go to the boundary of the moduli space if we were to compactify it. So that's kind of the crucial point. All right, that was an interlude into 2D TFTs. For those of you who are familiar with Lurie's work, you might wonder, how is this topological? This has to do with the fact that the space of diffeomorphisms of a topological surface has a homotopy type of the classifying space of if you take the group of diffeomorphisms of a topological surface of type GKL, that is that classifying space is homotopic to MGKL. All right. So it's the extension up of the purely topological field theory that brings in these singular chains. All right. Later on in 2005, Kevin Costello defined the things that we wanted, namely, you give me a bunch of classes alpha 1 up to alpha n, and tau I1 and the integers I1 up to In, and a genus and in which you want to compute. He defined some numbers like these. These are numerical invariants associated to a cyclic, smooth, cyclic and Calabi-Yau means the same thing. Sorry for interchanging the terms. Any smooth cyclic A infinity algebra A and a splitting of the Hodge filtration. I will go over the splitting right now, but the main point is that all you have to do is replace what before used to be cohomology classes on the target space. Those get replaced by Hochschild homology classes of the category. So in everything we do, we are trying to do stuff categorically. So we think of having been given a category or an A infinity algebra that replaces your original space. And now you need to know what other things in the theory get replaced by in this new context. And his construction goes exactly through this 2D TFT associated to the A infinity algebra. All right, so let me now, since this is an audience that might not be familiar with these topics, let me go slowly and talk about some of these concepts. So what is, first of all, a cyclic A infinity algebra? They are a homotopy generalization of the notion of ordinary algebra. We relax the associativity constraint. In a usual algebra, we say we want x times y, everything times z to be equal to x times y times z. Here we say we would like this to be equal, but only up to an exact, up to a closed term. So we have a notion of differential, and we're working in the DG world, so we can say two things are not necessarily equal, but they're homotopic. So if you want to give a cyclic infinity algebra, you need to give me a graded vector space. You need to give me operations mk. Now we have operations with more than one input, perhaps, of a certain degree. And they satisfy certain generalized associativity axioms, which can be best understood as related to disk bubbling in Gromov-Witten theory. And you need to have a non-degenerate pairing, which must be compatible with these multiplications. We think of this as exactly generalizing the notion of pairing from a Frobenius algebra. The cyclic operations, by which I mean, so now you can define something called cyclic operations, maybe ck plus 1 of x1 up to xk plus 1. It's you take mk of x1 up to xk and you pair it with the last one. So this combines the multiplication, one of the cyclic multiplications with one of the A infinity multiplications with the pairing. The reason these algebras are called cyclic is because you want these tensors to be cyclic. So this is exactly analogous to the condition xy comma z equals to zx comma y for a Frobenius algebra. So we generally will represent one of those cyclic multiplications. Actually, I should have written there ck plus 1 as what goes into a disk where you label the n points on the boundary by n elements of the algebra. This is what would happen when you count disks in a Fukaya category. And we know that these can bubble, and this is what gives rise to the associativity axioms. All right. So how do those cyclic infinity algebras arise? If you give me a Fukaya type category, they naturally come up. When you present a Fukaya category, naturally comes with cyclic infinity multiplications. If you have a Calabi-Yau variety and you want to take your category to be the derived category of the variety, it's known that there always exist generators of the category. And if you compute the endomorphisms of that generator in a DG way, and then you do homological perturbation to get an A infinity algebra, you will obtain a cyclic A infinity algebra homotopy equivalent to the original category. Think about this as a fancier version with more homological algebra of the usual famous result of Beilinson, that you can write the derived category of Pn as the algebra of endomorphisms of O plus O of 1 plus O of 2 plus dot 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 plus O of n. Right? There are no higher multiplications because this sequence is a sequence that has no x between the various pieces. It's an exceptional collection, but if you do this for a Calabi-Yau, you will get higher multiplications. So if you want to know such a cyclic infinity algebra explicitly, if your space X is a Calabi-Yau, is an elliptic curve, the simplest kind of Calabi-Yau, then you look up, and Polishchuk has done the hard work for you and wrote down a cyclic infinity algebra for you. And Junoo too wrote a beautiful paper in which he describes a recursive procedure where you can write a cyclic infinity algebra associated to any hypersurface in Pn, Calabi-Yau hypersurface in Pn. So the upshot of this discussion is that if you want to turn a space into a cyclic infinity algebra for reasonable spaces, you can, in principle. I mean, these formulas get incredibly complicated, but they're known. And in the case of matrix factorization categories, for those of you who know what's going on, you can take K-stab, the stabilization of the residue field, as a generator. You take the endomorphisms of that, and Dijkhoff computed some of the higher multiplications, and then Junoo too computed this for a homogeneous potential. This is related to the previous result. In any case, the main point is that the first step in computing some categorical enumerative invariants is to take your category that you're interested in and distill it into a more manageable form, which is a cyclic infinity algebra. And this, you somehow hope that somebody else has done the work for you. It's not a uniform method, but for reasonable situations, we have information on how to do this. Now, let's go back to this statement of Costello. This was the most important realization that he had in his paper, that you cannot define enumerative invariants purely from a Calabi-Yau category. Just having the Calabi-Yau category is not enough. And this was missing from Kontsevich's original formulation of how to go from homological mirror symmetry to enumerative mirror symmetry. So if you remember one thing from this talk, I hope you will remember this, that you need more data. And this data is this splitting of the Hodge filtration, this kind of abstract, I'm saying words here, but you need more data. The algebra A you should think of as just your category. It doesn't contain more or less information than it. But the splitting is an extra choice. It's something that you need to make a choice, and you get different results for different choices. All right. So what is this splitting? So I'm going to give you an explanation what this splitting is in a geometric setting. Namely, let's say we are studying the derived category of an elliptic curve, the simplest kind of case. If you write down any elliptic curve that you want and you take its derived category, from this derived category, you can actually extract a short exact sequence, which looks like this. It has H10 is a sub of H1 de Rham, and H01 is a quotient. The middle space is two-dimensional. The outer two spaces are one-dimensional for an elliptic curve. But the most important point here is that while H10, the first term, sits as a sub, H01 does not naturally sit as a sub in in the de Rham cohomology. H01 is a quotient of de Rham. And choosing a splitting is exactly choosing a way to write the de Rham cohomology as a direct sum of the two pieces. You already have one sub. You need to write a choice of embedding H01, the third term in the exact sequence, into H1 de Rham. Now, you might ask, okay, how does this have to do with categories? You said you were going to do categories, but in fact, you are doing elliptic curves here. There is a way to phrase the problem completely categorically, namely, if you write the cyclic homology, there's a spectral sequence whose E1 page has cyclic, I wrote it backwards. I apologize. This has to be corrected. The correct thing is the right-hand side converges to the left-hand side. My bad. I wrote this late last night. but so Hochschild converges to cyclic homology. Hochschild homology is something that has terms like H10 and H01. We know that this spectral sequence degenerates at E1 by work of Kaledin, proving a conjecture of Kontsevich. Once you get that, you know that there will be a filtration of cyclic homology with factors Hochschild homology, and that's exactly the statement that there's a filtration of the Ram cohomology, which is cyclic homology, whose factors are things like Hodge cohomology, H10 and H01. All right. So now let's go back to the geometric setting. What you need to do to give such a splitting, it's enough to tell me what should be the image of H01 in H de Ram under the splitting. So this goes back to old work by Witten, this interpretation, that Witten said that we should, one thing we should study when we study mirror symmetry, say for the mirror quintic, we have a Lagrangian, we have a symplectic space H3 of any quintic, H3 de Ram, that has the intersection pairing, which is Q-symmetric, that makes it symplectic space. We have two Lagrangians in there. We have one obvious Lagrangian, which is H30 plus H21. That is a Lagrangian. But H12 plus H03 is a quotient, and we need to tell you need to tell me how this Lagrangian gets embedded. So what you should think of as this splitting choice is you don't need to choose the splitting only at one point. It's enough to do it at one point if you want to compute the value of the number f0 of c or fg of c. But if you want to get a generating function, you need to choose a splitting everywhere on the moduli space, or at least in the vicinity of a large complex structure limit point. And now I'm going to tell you how to do that. So there are different ways in which you can choose a splitting. So here's the first one, which probably has been on anybody's mind who has been following, which is called the complex conjugate splitting. Anybody who read Griffiths and Harris knows that usually we write the de Ram cohomology of an elliptic curve as H10 plus the conjugate of H10, which is isomorphic to H01. So we can take L2 to be the complex conjugate of L1. It never aligns with so for an elliptic curve, the space H10 is never real. So H10 conjugate is not equal to H10, so you can take it as a complement, i.e. the image of H01. If you take this choice, there's some good stuff about it. Namely, it's defined everywhere. I did not make any choice away from the elliptic curve. I can just say, okay, here I am in the moduli space, here's my splitting. I go somewhere else, I compute the splitting there. Because I compute this everywhere in a natural way, this splitting is modular. It's defined everywhere on the moduli space of elliptic curves. However, this does not vary holomorphically with psi, with a coefficient of the elliptic curve. So if I'm going to compute something using this splitting, the answer will not be a holomorphic function of psi. This is going to be a bit of a problem because we are hoping this FG of the family of derived categories, we would like this to match the generating power series of Gromov-Witten invariants, which is by definition holomorphic. We just write it as some power series in Q. So it has no Q bar. Still, it's a splitting. It's interesting. It's good for us to know that it exists. intuitively, this works by saying that we write H1 the RAM as having two basis elements, one being dz, one being dz bar. All right. I'm going to give you now another splitting, which is called the monodromy invariant splitting. You say, I've fixed a special point in the moduli space where there is monodromy. And I'm going to use the concept of monodromy to fix a particular splitting. Namely, I will want my splitting to be invariant under monodromy, under parallel transport via the Gauss-Manin connection around the large complex structure limit point or an orbifold point. If I do this, the answer is a holomorphically varying splitting. But because my moduli space has got several interesting points, I cannot talk about monodromy without fixing a small disk around the large complex structure limit point. If I go too far, there can be several cycles possible around the large complex structure limit point that will not be homotopic to each other. So this is why it's not modular, but it's holomorphic. I wrote down here a formula for the the image of H10 is dz minus dz bar over tau minus tau bar. All right. So now I want to give you a little bit of a feel for why this splitting is needed in the theory. So you know now that you can compute some kind of invariance associated to a family of Calabi-Yau categories and a splitting. But you might ask, okay, where does this splitting go into the calculation? And I'm going to give you a very kind of impressionistic point of view, but try to bear with me for a minute. So let's say I'm trying to compute one of the simplest possible invariants, namely a 1-1 invariant. So I am looking at stable maps from curves, from elliptic curves into some target manifold, if you want to think of the geometric setting. So instead of doing calculations on M11 bar of x beta, I can do my calculation, I can move all my calculations just to M11 bar. By pushing forward from M11 bar x beta to M11 bar, I can, to compute a Gromov-Witten invariant, I can reduce my question to integrating a particular differential form on M11 bar. So I pictured here M11 bar. Everybody knows it's P1. So if we ignore problems of stackiness, it is the same thing as a sphere. It's compact. It has one point that has been added to it on top of the usual M11. It's a point where the elliptic curve degenerates to a node, to a nodal cubic. And now to calculate a Gromov-Witten invariant of this type, we need to integrate over the whole sphere some differential form. I wrote there, here, alpha is some insertion. I need to have an insertion because I'm in 1-1. And if you are familiar with the Kontsevich-Manin Koch-Ft approach, this is the Koch-Ft value on that form. So if I wanted to know the Gromov-Witten invariant, I would just need to carry out this calculation. And this is classical Gromov-Witten theory. I'm going to break down this calculation of this integral as a sum of two pieces. One is the integral over A. A is this red hashed area here, which is I've taken out a small open disk around the cusp. And the integral over B, over whatever is left, this blue region. So the first integral turns out to be easy. This is something that the extended TFT just straight up gives us how to calculate. I told you that the extended TFT told us how to calculate stuff about chains on moduli spaces. And this A is a chain in M11. M11, not M11 bar. it's one of those chains that I had there. So I can calculate this integral directly from the extended TFT. This part, however, cannot be computed from the TFT because it involves stuff about the compactified moduli space. But the way I could hope to calculate the second integral is if I knew somehow that this differential form was exact, it was the boundary of another form, I could use Stokes and calculate the integral over B as an integral over the boundary of B, which still is an integral inside the moduli space without compactification. So this again can be computed out of the TFT. However, there may be many choices of this omega 1 prime. So just saying that somehow this is exact does not tell me what omega 1 prime I choose. And the specific choice is exactly the choice of splitting somehow. This is where the splitting goes. All right. Now let's get to the current day and age. Costello conjectured implicitly, okay, 2 more minutes. Costello conjectured that if you work with a Fukaya category and you use the monodromy invariant splitting, you should compute Gromov-Witten invariants as kind of predicted by what you wanted to compute. However, his conjecture laid completely dormant for 15 years because it was impossible to compute anything. His definition of his categorical invariance was completely non-explicit, and you could not compute anything in the theory. The new result with myself, Costello, and Tu in 2020 was we gave a different formula for Costello's invariance, which is a combinatorial construction which can be in principle computed. You give me an A infinity algebra and the splitting in some explicit way. I'm not going to tell you how to do it. There exists an explicit algorithm to compute these invariants. And even though I say this is computable, you need a computer the size of the universe to do real computations. But we can now verify Costello's conjecture for elliptic curves, basically, up to genus 2, and soon I hope to do it for genus up to 5 with new tools. I want to end by explaining how amazing it is, the fact that we can use different splittings. And with this, I will stop. The fact that in this theory, we can put in different splittings is actually an extremely powerful tool. So I've depicted here the moduli space of complex structures on elliptic curves. So think about it as here is the cusp, tau equals to I infinity, the large complex structure point. Here is the orbifold point, tau equals to e to the 2 pi I over 6. I can talk about monodromy around this point. And that will determine some splitting. The monodromy invariant splitting is defined only in the neighborhood of this point. I can talk about monodromy invariant splitting here, and I have another splitting here. And I have the complex conjugate splitting, which gives me some strange result, and it's defined everywhere. Now, the point is, we have ways to say, if I go from one splitting to another, how the potential, the Gromov-Witten potential changes. And so if I compute with the red splitting, I get the Gromov-Witten invariance. If I compute with the yellow splitting, I get something else, but I can relate the two. And turns out that comparing the red and the yellow turns out to be the holomorphic anomaly equation in Gromov-Witten theory, which for classical Gromov-Witten is very hard to prove, but for us, it's less than a page to prove. Moreover, because the yellow splitting is defined everywhere, I can compare what I get in the Gromov-Witten theory here with what I get in the blue theory here, which turns out to be FJRW theory. So if I want to compare Gromov-Witten theory to FJRW theory, in other words, to do Calabi-Yau Landau-Ginzburg correspondence, all I have to do is compare the calculation in the red splitting with the computation in the yellow splitting, extend the yellow splitting up to this point, which makes sense, and compare it with the blue splitting and get the Calabi-Yau Landau-Ginzburg correspondence. Okay, I've put here a number of current results and open questions, but I will stop here and I'm happy to answer questions.
Thank you. We have time possibly for one quick question. Okay.
My question is that given an cyclic infinity algebra, we can naturally define the corresponding Maurer-Cartan theory such that its endpoint functions are exactly naturally, they're just these things. How is there any way that these actions and classical theory fits into these things?
I'm not sure I know how to answer this.
Because you said that your calculation is by homological perturbation lemma, and it's just exactly what is used to calculate Feynman diagrams and so on in infinity algebras.
The Feynman diagram, maybe let me say that the Feynman diagrams involved in computing Gromov-Witten invariants are a combination of calculations with real Feynman diagrams and this topological field theory extracted from the infinity algebra. So the infinity algebra gives me the field theory, and then the way to extend this field theory to spaces which have singular stable curves is done using Feynman diagrams where the propagators involve the splitting. So the infinity algebra goes into defining a field theory that's defined only on smooth curves. And then to extend it to singular curves on the boundary of the moduli space, I need to know the splitting, and that will be put as a propagator on the Feynman diagrams. I don't know if this helps, but.
Okay, thank you. Then let us thank the speaker again. So now we should have another